Homogeneous charge compression ignition, quite literally, is a uniform mixture of air and fuel that is ignited through means of raising the heat using spontaneous ignition. As of right now, this technology is not yet in production, but is providing many new technology concepts for moving forward towards efficient, low-emission internal combustion engines. Diesel engines have stratified or heterogeneous mixtures. This means throughout the cylinder there is very little mixing of air and fuel. Due to this, diesel engines have very rich areas of combustion and very lean areas of combustion. Because of high heat and high oxygen content, diesel engines tend to burn very efficiently. The fuel type and the high heat create large quantities of particulate matter and large quantities of oxides of nitrogen, both of which are difficult and expensive to control. Gasoline or spark ignition engines are a heterogeneous mixture, meaning that a mixture is consistently mixed throughout. The air-fuel mixture is consistent and can provide relatively stable combustion temperature and relatively low emissions. The byproducts of these emissions are mainly hydrocarbons and carbon monoxide, both of which are relatively easy to control through catalytic converters. The idea of HCCI is to use the best of both worlds, to have the emissions of a gasoline engine and the efficiency of a diesel engine. Stratified fuel engines are generally compression ignition engines. The basic idea behind these engines is to fill the cylinder with as much air as possible and then compress it to create heat. Once the air has a high enough sensible heat, it can inject the fuel. The fuel entering the compressed air will self-ignite from the high temperature at the outer edges of the fuel spray. As the outer edges of the fuel burns, it will eventually progress through burning all the way through the fuel. There is generally far more air than needed for combustion. This creates a slow but high heat release. Very little fuel is used to create heat release in these engines. Due to the large quantity of air the fuel is injected gets used in its entirety. Downfalls of this system include the following. The high compression ratios create a lot of resistance to turning the crankshaft. High fuel injector pressures involve having to turn a pump at up around 30,000 psi max, and having extensive injector fuel systems. High combustion chamber temperatures create lots of oxides of nitrogen as well. Homogeneous mixture engines are typically spark ignition style engines. They have relatively constant mixture that gets let into the cylinder. The amount of air-fuel mixture that gets let in is dependent on power output requirements. That mixture will be compressed and ignited by way of spark. The mixture will burn from the spark outward in a wave-like pattern. Because of the spark igniting the air-fuel mixture, it is very easy to control the flame timing and the location of the flame front. The areas of the combustion chamber that are close to the cylinder walls, piston and cylinder head, are considerably cooler and experience a poor flame production at these locations called quench areas. The hotter the combustion is, the smaller the quench area will be, but the more potential damage that can occur to the engine and mechanical components. These areas are required to protect the items from overheating and melting, but these areas also have unburned and poorly burned fuel. Hydrocarbons and carbon monoxide are a result of this. However, a catalytic converter can easily control this. Gasoline engines always run at set air-fuel mixtures close to 14.7 to 1 in order to have proper combustion, which makes it difficult to lower fuel usage and be as efficient as a compression ignition engine. Homogeneous charge compression ignition advantages and hurdles. The idea of HCCI is to have low particulate and NOx emissions while having low fuel usage. Although homogeneous mixtures will have HC and CO emissions inherently, current technology can easily control them through catalytic converters. Fuel can be burned extremely fast due to spontaneous ignition throughout the mixture. This would also allow the air-fuel mixture to have low fuel content, have a very efficient engine while still having great power output. Also, due to the homogeneous charge and the rapid burn, it would be much cooler than a stratified combustion and even cooler than a traditional spark engine. This would result in low NOx emissions. As compared to current model gasoline engines, some prototypes are claiming a 15 to 40% increase in fuel efficiency with the same power output. The main hurdle with homogeneous charge is that in order to reduce or control the engine output, the quantity of the mixture must be limited. If there is less air-fuel mixture entering the combustion chamber, how are we going to get the compression needed to ignite the mixture? This engine will effectively need to create the correct amount of heat needed to cause spontaneous ignition relative to the amount of air-fuel mixture let in. Some engine strategies to achieve this have been variable compression engines, variable intake control, variable exhaust gas recirculation, and variable valve timing. One interesting fact about HCCI is its compatibility of fuel usage. Because of the variable nature of the fuel and the variable nature of the engine, any combustion can occur as long as it's hydrocarbon. The engine controls simply have to modify the programming to adapt the present fuel's spontaneous combustion point. Here are some existing prototypes of HCCI engines. The GM Ecotec, already in the testing phase and having several driving prototypes, the Ecotec engine has a mild version of the HCCI concept. Although this engine still needs spark plugs for starting when cold and high power output, it still has the capability of running in HCCI mode during cruise and light to mid-load conditions. It does all of this with very mild changes to the engines. The main difference is this engine runs an early closing of the exhaust valve. By closing the exhaust valve early, it traps a large quantity of burned gases in the combustion chamber. The exhaust gas heat is then used to raise compression pressures and compression heat in order to have spontaneous combustion occur. During predetermined conditions, this could occur anytime the engine is running, but not at high power or load conditions. GM claims it works from idle up to 60 miles per hour. Even though this is a very light version of this fuel combustion delivery concept, it is said to increase its economy by as much as 15 to 20%. The best thing about this system is that it does not need major changes to the engine design or operation. It should be able to be integrated somewhat easily into many engines and designs that incorporate variable valve timing. When this system switches from spark mode to HCCI mode, it even sounds like a diesel engine. The major reason we have not seen this system yet is they have not been able to control the system well enough to have the proper exhaust in the cylinder and the proper fuel mixture as well. It still has poor operations in some climates, very cold and high altitudes, but when the programmers get their stuff together, it should become available to the general public. This first edition of the HCCI is projected to be released in 2012 from General Motors. Also, Mercedes-Benz has created an engine they called the Diasoto, which I believe is a mixture between diesel and auto, that operates with very similar properties to the GM Ecotec. These engines require pressure sensors in the combustion chamber. This new technology is the major step towards more efficient engines. The pressure sensors in each individual chamber can be utilized to adjust individual cylinders for proper output and ultimately perfect engine cylinder balance throughout. In the HCCI engine, it is a required technology in order to achieve the correct pressures for spontaneous combustion. Although a scissor-like engine block that can change the position of the crankshaft relative to the cylinders seems to be a better control method, it is very weak from an engine block design and extremely expensive. As well, the fast intake temperature change has been experimented with. It involves combining hot and cold air in a variable combinations, and this is also in the beginning phases of HCCI. The variable exhaust closing system seems to be the way most manufacturers are going. Due to the new fuel economy regulations being put in effect by President Obama, the manufacturers have to find a way to produce less CO2, less oxides of nitrogen, and still use existing infrastructure for fuel delivery. This system seems to be a short-term solution to all of these concepts. Expect to see it coming in the near future.